These are the answers to page 628. We're doing comparison tests, and the first 4 here ask us to do a direct comparison. So what we're trying to do is figure out a series that would be similar to this. So 1 over 3n squared plus 2 is going to be similar to the series 1 over n squared. That's the principal piece of this one. So we kind of ignore the 3, forget the 2. And what we want to do is when we compare, we want to make sure we know what this series does. So n squared is a p series that converges. All right, so we know that this series converges. And then we look and say, all right, well, 3 times n squared plus 2, that's going to be something bigger than just n squared. So these denominators will be bigger than these denominators, which will mean these terms are smaller than these terms. This sum will be less than this. So this sum here that we weren't sure about, we know for sure is less than this one, which converges to some number. Therefore, this also must converge. So we would say that this series converges by direct comparison to 1 over n squared. If we had found that it was greater than 1 over n squared, that would tell us nothing by direct comparison. Same thing here, we've got 1 over 3 to the n plus 1, so that in principle is the same as 1 over 3 to the n. That's a geometric series that also converges. Okay, so then I look and say, well, 3n plus 1 is slightly bigger than this, so these denominators are slightly bigger than these, which means these terms are slightly smaller than these, which means this sum is slightly smaller than that one. So since this is something smaller than this and this converges to a number, then this must also converge. So this converges by direct comparison to 1 over 3 to the n. I look here, I've got 3 to the n over 4 to the n. The 5 really doesn't matter. This is going to be similar to 3/4 to the n, or 3n over 4. 3 to the n over 4 to the n. Now that's a geometric series that converges. And when I compare it here, this 4 to the n plus 5 will make these denominators slightly bigger than these denominators, which means these terms will be slightly smaller than these terms, which means this sum will be smaller than that. So again, by the same logic that the other two were, this series converges by direct comparison to the geometric series 3/4 to the n. And then we get to 14, and we've got 4 to the n over 3 to the n minus 1. Now that's going to compare to the geometric series 4/3 to the n. 4/3, if you keep multiplying by 4/3, 4/3, 4/3, that actually is going to get bigger and bigger. This is a divergent series now. And when I look here, 3 to the n minus 1, that's a slightly smaller denominator than this, which means these terms will be slightly bigger than these terms. And that means this sum will be bigger than this sum. And if this sum is going to diverge and go off to infinity, and this is going to be something bigger, then this also will diverge. Right? So this diverges by direct comparison to the geometric series 4/3 to the n. So it's really nice and convenient if we see, what this principal piece would be, and if we can see a direct comparison. Boy, that's really nice. But not always does that happen. Like in 16, we would probably compare this to 1 over 3 to the n. But if you compared it to there, these denominators are smaller, which means these terms are bigger. So you get a bigger sum than a convergent series. There's no logical conclusion to that. So what we do in these cases is we still compare it to 1 over 3 to the n. There isn't a better series to compare it to. But now we're going to use a limit comparison. And what limit comparison says is go ahead and take the general term here of what you have divided by the general term of what you're going to compare it to. And let's take the limit as n goes to infinity of that. Right? And so if I flip this over, I get 2 times 3 to the n over 3 to the n minus 5. I'm taking the limit as n goes to infinity. And you can see again, over time, this minus 5 isn't going to mean much. These 3 to the n's are going to cancel each other out, and we're going to end up with 2. So over time, this sequence, this comparison, this ratio here, will go to 2. Now, what limit comparison test says is as long as that limit goes to anything other than 0 or infinity, then these two series will agree. So since this is a convergent series, this also must converge. So it converges by limit comparison to 1 over 3 to the n. If we would get 0 or infinity, that means that we picked a bad thing to compare it to, or perhaps limit comparison isn't going to work for us. Right? So I see here, I say I got n squared on the top, n to the fifth on the bottom. So if I just kind of boil it all down, this is very similar to 1 over n to the third, which is a convergent series. Okay. Now again, I can't compare. There's too much going on here to know which one's bigger or smaller, so I'm just going to go ahead and take the 2n squared minus 1 over 3n to the fifth plus 2n plus 1 and divide it by that 1 over n to the third. And I'm going to take the limit as n goes to infinity of that. So if I flip that over and multiply, this gives me the limit as n goes to infinity of 2n to the fifth minus n cubed over 3n to the fifth plus 2n plus 1. So those n to the fifths are the principal pieces. All this rest of the stuff doesn't matter. And since they're the same degree, this is going to go to a limit of 2/3. And so we did get something not 0, not infinity, and that means that these two series then are of the same magnitude. They're going to do the same thing. Since this converges, our series converges. So we'd say it converges by limit comparison test to 1 over n cubed. Here I've got n squared. If I were to work that out and look at it, it would be of the same magnitude as 1 over n cubed. Again, I might not know exactly how to compare it or not be confident with that, so I'm just going to go ahead and I'm going to multiply that out, distribute that out, and then go like that. And I'm taking the limit as n goes to infinity of that. So that's going to be the limit as n goes to infinity of n cubed over n cubed plus n, which equals 1. So again, I got an answer that's not 0 or infinity. So this is, this converges by limit comparison to 1 over n cubed. 23, if I were to take the square root of n squared, I'd get n times n would be n squared. So again, in terms of boiling it down to what its principal piece would be, n squared would be what that kind of looks like, and that's a convergent series. All right, so then if I say, well, I'm not sure how it compares, but if I go 1 over n squared of n squared plus 1 over 1 over n squared, take the limit as n goes to infinity of that, flip that over, I get n squared over n times square root of n squared plus 1. Take the limit as n goes to infinity of that. And as n goes to infinity, this plus 1 becomes insignificant. We're going to get basically just n squared on the bottom over n squared there. This limit's going to go to 1. And so since it does give us a number, not 0 or infinity, we would say that this converges by limit comparison to 1 over n squared. All right, and the last one here, we've got n over n plus 1 times 2 to the n minus 1. Now these n's you can kind of see aren't going to do much over time. They're going to kind of neutralize each other. So really this is going to become similar to this 1 over 2 to the n, which is a convergent geometric series. All right. But again, to be able to compare them directly, that might be a little tricky. So we take the n over n plus 1, 2 to the n minus 1, divided by 2 to the n. All right. We take the limit as n goes to infinity of that, which is the limit as n goes to infinity of, flip it over, sorry, this should be 1 over that. It should become 2 to the n times n over n plus 1, 2 to the n minus 1. All right. Now, this n plus 1, as n goes to infinity, that's going to become 1. So that's going to kind of go away. This 2 to the n is really 2 times 2 to the n minus 1. If you pull a 2 out of there to get the exponents to match up, then those are going to kind of cancel out. And so these are going to neutralize, these are going to neutralize. The only thing that you'd have left then would be a 2. Now, we got a number not 0 or infinity, so they're going to agree. Since this converges, so does ours. Converges by limit comparison to 1 over 2 to the n.